I will start recording.
Yeah.
Today, what I say? Yeah.
Is that about law? About law?
Better Call Saul. Law.
I saw
Like a Netflix
Yeah.
premiere film.
Okay, guys. I think you guys, while downloading these large folders I shared, I guess I can start a little bit first. So, RSA, representational similarity. I will take easy today, I'm not going fast. I'm not rush, okay? I will take slow. I will take easy stuff and chilling out a little bit. So, RSA is representational similarity analysis. And have you guys seen before or not? No? Just no answer. Okay.
Just saw it today, this morning.
Yeah, maybe. Not problem, but okay. Have you guys seen this TV series? It's really famous and actually really one of the best in TV history. Breaking Bad and Better Call Saul. Only Anna? You know that? Yeah. This is really good one.
Okay.
Yeah, you guys better watch it, okay? The thing is, I watching too much these days, and the thing, I watch it too much, and I didn't prepare presentation, so. I say, I know how to use it. My master thesis is really heavily rely on this method, and I have a lot of resource and application to use, and indeed we need a lot of toolbox, and yeah, we need some technique. We need troubleshoot a lot of some technical part for using this, apply this toolbox and use this method fluently. And so that's why I start by actually not really introduce about this concept part, but rather I want to start with this folder I shared actually. So I have this. If you take a look after extraction, these folders that I shared, they're already you will see at least seven toolbox.
Yeah, you don't have to.
Yeah, but I need it, so I included. Maybe you guys don't need it. Cosmo MBPA. Cosmo MBPA is the one that.
I also provided.
Yeah, that's cool. Cosmo MBPA is good for. I think in the morning earlier time, I guess Xiaoshan already have give explanation about MBPA.
Did you broadcast already? Did you broadcast already?
Yeah, I did.
Thank you.
So Cosmo MBPA is a toolbox for MBPA and RSA. And secondly, there is RSA toolbox. RSA toolbox is provided by the author of this manuscript, which is published in 2008, and we can we can just recreate all the figures provided in this manuscript. There's like really good, well-written demos and well-written examples. So we just set pass and run the demo manuscript, and we can just recreate all these figures, cool figures, and we can actually like they also have like second level inference of RSA, and this keep going on. And I have some other toolbox external dependencies for more applications. For example, LIB-SVM is for MBPA, but there was actually some request like to show how to use Cosmo MBPA. Like did Xiaoshan use what did Xiaoshan use?
Princeton, search one.
Princeton, search mode, okay. Cosmo MBPA is a little bit more flexible and can be used for general use. It's for more general use, and Cosmo MBPA is actually simple for me, you know. So I want to share it. I want to share about how to use Cosmo MBPA and how to use LIB-SVM and how to install and use for the SVM as a classifier. I think Xiaoshan used what, base, knife base, or LDA? GMB, yeah.
Knife base.
Yeah. So SVM is another classifier can be used for the MBPA classification. So I'll show about LIB-SVM part. And fMRI method, this is fMRI MATLAB toolbox. I think Professor Chen maybe know better, but it turns out that Cosmo MBPA actually, for the demo using, they requires to insert this fMRI MATLAB toolbox because they use their demo practice data set is actually fMRI data set. So I included in our folder and what? So and demo musician practice. This is one of my research data set that I heavily used for RSA and MBPA as well. MBPA search and RSA, I used these two methods for this data set. So it's for real data, so it's not demo, it's real data that I provided. But only part, like three subject, musicians. And I will explain what was the experiment and what's the task, what's the stimuli part, which is very important for RSA. And BrainMap Viewer is another toolbox for visualization part that I used for visualization. And their visualization is slightly different, and it uses a little bit of node and edge, this kind of looks like graphic theory based visualization, but actually, so it's just showing some connection between brain areas. Then that's it. So what? Cosmo MBPA. Is it okay to go on or need more time? Not yet?
With downloading?
Yeah, downloading.
Yeah,
Not yet. Too bad, okay? I guess. Then I will talk a little bit about concept then. RSA concept. RSA, representational similarity analysis. Need to understand what is the, first it requires to understand what is it is one of multivariate analysis. And it comes later than MBPA actually. So it was 2008, and later early 2010s, there was another applications, and it still be used by many other researchers for carrying out analysis for fMRI, and also including EEG or other modalities based. So what's the strength of RSA is because RSA transfer our data into this relative dissimilarity space. It's called representational space. And so we use similarity as a measure to representing how the data between stimuli is different. I know it's not intuitive, but actually in computation it's not that complicated. So, okay, let's see this part. So I will keep talking about dissimilarity matrix, and this is like a basic unit we use for the RSA. This dissimilarity matrix encode relative differences between stimuli. So we have, for each task in the experiment, we can have like a lot of stimuli, a lot of condition, and subdivided by a lot of stimuli. Like, for example, we have like 4 conditions divided by 20 stimuli, 5 for each conditions, and each stimuli actually can represent different value. And how we're going to measure dissimilarity between stimuli is another question. But at least we know that stimuli, for example, we have in this experiment we have these 2 conditions, face and house, subdivided by 2 different face, male face, female face, and 2 different house. It's what? It's like house. What is this? Like a mansion or something? I don't know. But so this in dissimilarity matrix, we can at least intuitively understand that between face there is less dissimilarity compared to house, right? House stimuli, face stimuli. There's a male face, female face. There is this difference. There is difference, but at least this difference is less than compared to house. Some like a house and face. So that's what dissimilarity matrix actually representing. Like male face to male face is zero difference. Male face to female face is like a slight difference, and male face to this house is very significant difference. Male face to this house is like a little less, but still very positively dissimilarity. So that's what this color actually encoding. And dissimilarity is the value between 0 to 1. And for example here, compute dissimilarity use the correlation. This is called correlation distance. 1 minus correlation across space. So we calculate correlation. So because we have stimuli and then we have a lot of trials for the experiment task. For example, like for each like a male face, we have 100 trials. Female face, 100 trials. House 100 trials. House 200 trials. We can compute the correlation, right? 1 by 100 vector for each stimuli. We compute correlation between stimuli, and then 1 minus this R correlation is the correlation distance, which is turned into 0 to 2 actually. Yeah. But it can be 0 to 2 can be scaled, normalized scaled to 0 to 1, and it will be correlated to our model reference candidate metric, candidate RDM. Yeah. So that's the RSA. So RSAs have some strengths in like different modalities and different hypothesis-based models and behavioral data. Like all this kind of data based upon same stimuli, same design, can be transferred into the same space, and then we can compare by correlation across these datas. So previously, like we cannot like just compare like fMRI brain data to the like behavior responses. Like you cannot just correlate these two, right? I mean, we can, but like not easy, like maybe. But in like a whole design context, whole stimuli context, we couldn't really do it. But RSA actually in the RDM, this matrix space, we can do it because it's all in the same matrix, like a stimuli by stimuli matrix. For example, like 20 by 20 stimuli matrix. We can just behavioral data can be computed 20 by 20 this stimuli matrix. brain activation, 20 by 20 stimuli matrix, and we just compare these two metrics, and we can just summarize it into just one R value. And this R value later can turn into some summarized in statistics, and that's cool then, right? So that's what this manuscript actually suggesting, like they.
How do they compute the correlation between two stimuli? For instance, suppose they have 20 male faces.
Yeah.
And 20 house mentions. So how do I compute that similarity correlation? Do I use the single trial betas?
Yeah. For the brain activity, they strongly recommend to use trial estimate and beta.
Okay.
Right? So for
based on
each trial.
So they're based on the 20 beta and the 20 betas to compute the correlation between those two stimuli.
So we always have stimuli, and we always have more trials basically. So at least like that's how experimental design is supposed to be. So you can just average it already. Anyway, so this paper used many different input, computational model, other modalities, monkey cell recordings, monkey fMRI, human fMRI, blah blah blah, right? And like across different ROIs. So yeah, this relative distances is what they measure and we compare right now. So here we have at least, so there is like actual distance measure. Is there a lot of different kind? Euclidean distance, correlation distance, name it. Like I know, like there's another one famous one, but what?
Yeah, it's hard to pronounce. Forget about it.
Oh, yeah. I forgot it.
Mojave is.
yeah, Mahalanobis. But each measure of distance is slightly different in computation way, and some is univariate and some is multivariate, and that's a part we may need to discuss. But usually we use correlation distance in conventional way, because the correlation distance is multivariate. Anyway, so there's like these three, and in here we have these four conditions. It look like each dot representing, I guess, each stimuli, and each stimuli distance is shown in this figure, I guess. In the Olivier cortex, how it look like face and natural objects. Yeah.
I don't know how to read this figure.
Yeah. Nah, I think not yet, I guess, but at least in the right FFA we can feel that face is clusterized in certain area, and it representing this face stimuli is actually close in the right FFA activation. The face stimuli are actually represented as like a close distance compared to like a natural object. Is like you can see this, but dispersed. This relative distance is like much closer in the in the face of right FFA activation. So this plot is called MDS, multi-dimensional scaling, and it shows relative distance across stimuli or across condition or whatever. And it's kind of descriptive. It doesn't really quantifies the statistic or like how far between stimuli. Not yet, but later. Yeah. So here is their stimuli, I guess. And is there like hypothesis for how this image actually represented in a different like a computation model, or this visual image processing. So they hypothesize like a Vuillon simple cell actually. Vuillon simple cell see this image like this, and Vuillon complex cell actually see this image like this. Maybe, right? And radon is like, I have no idea what radon is, but that's how this image actually look like in terms of radon. So this is like a stimuli, how represented in each different condition, and later this condition can be represented in the RDM in this way. We have 96 stimuli, so this each matrix is 96 by 96 matrix, and so there is like a different different representation for each each model, each dissimilarity matrix. What it tells us, this model is artificially created, and this is like what researchers generated based on their hypothesis or based on their thinking, computational model, or as simple as like this, like animate versus inanimate, which is comparing the condition. So animate, I guess first 48 stimuli is animate, I guess 49 to 96 is inanimate, and this simple dissimilarity matrix tell us 1 to 48 is no dissimilarity, zero dissimilarity. Meanwhile, 1 to 48 to 49 to 96 stimuli is highly dissimilarity, dissimilar to 1. This is like coding animate versus inanimate. Meanwhile, there is something else, phase, non-phase dissimilarity matrix. I guess this is like what? 48 by 12, like 30 to what? 24? 30 to 24. And I have no idea. I'm bad at improvising these things, but
So that's just curious for clarifications by the terminology used in RSA. It's quite mind-boggling when I also first learned how to understand these concepts. And so I think it's probably essential to clarify the concept used in these realms. For example, when you say model, because when I saw the upper left, like you go up a little bit, you see a V1 model. So what does it mean to be a model in this case?
I think this real model is not from brain activity, it's from their
You're talking
model.
about like from V1's perspective, right? I mean, if you consider yourself like a V1 cell, and what you look at, because you show us some of images from V1 cell, from V1 complex cell, like the output of these cells consists of some kind of, like abstract stuff, map or whatever. And to me, it seems to be an analog of the model, because we actually don't know how to best define what's a model. Model is some kind of proxy to the real world. But that distance to the real world, how vivid to the real world, could vary a lot between different models. V1 model is a very like early phase of visual processing, so it encodes, we know, like luminance or light intensity and stuff. E2 cells, a little bit of contrast difference or some kind of so-called image statistics. So it's like what's that? It's like a proxy to the real world. But we as a human used to see the real world as like a real world, like this is what we understand as a real world. But from different cells, from different levels of I don't know, different layers or different levels of processing is quite different. I think it's that model is something that we should at least clarify here, or at least talk a little more about here.
Okay.
And then you can move on to how to define the so-called horizontal axis or vertical axis and others. Because I mean, we used to, as novices, understand RSA in terms of the colorful grid. But we don't know what consists of this, because it is very flexible to my opinion. Like it could be cell, it could be stimuli, it could be whatever.
But let me be clear, like this model is arbitrarily like defined by the author, and here they provided the explanation of what is real model in their methodology part.
Okay.
Which I'm not sure. What is it? Receptive field of simple cells simulated by Gabor filters, blah blah, I guess. Yeah. I think it's I think it's through the image processing and
No.
coding some filter and then get the values from the stimuli itself, I guess.
Yeah.
Yeah, not the brain activity or real cell
You
recording.
can
no.
use like single cell, multi-cell, or various kind of measures from monkey, from rats,
Yeah.
from
Mhm.
whatever.
Yeah. Yeah. So yeah, this part is it's hard for definitely.
You want to give us a quick walkthrough, right?
Yeah, I will. So keep. I think like I will go on, but first. So this RDM, how? So this RDM is from brain activity, left FFA, right FFA, left PPA, right PPA, EPC. So now we represented all these different kind of cross-modality data or model-derived data into the same space, 96 by 96 space. Now we can actually just compute correlation between these RDMs and tell which RDM is actually more close to each other, or which RDM is like more, representing the same things. So we can just we can already see that left FFA, right FFA already quite similar in this matrix format. Meanwhile what? Left FFA, right FFA, and face non-face, face animate prototype pattern, it looks kind of encoding the same patterns at least. Left PPA, right PPA, this dissimilarity is looks similar, and animate it might encoding some of this similarity in the correlation terms later, I guess. So this, I think right now it turns out. So it turns out this plot provides the correlation, deviation from the Olivier cortex dissimilarity matrix, 1 minus Spearman correlation. I think it's showing the what is the deviation is dissimilarity, so it's less is close, high is distance. So I guess right FFA, left FFA was best, which is most close. Like a radon RDM was like a most unsimilar. Meanwhile, there is this kind of the RDM by RDM. So we have like 3, 4, 5, 1, 2, 3, 4, 5, at least like about like more than 20 RDMs, and this RDM by RDM cross correlation matrix can be calculated, and it's the same the MDS. It shows the relative distance between the RDM. So this is our second level. So first level, we have some idea of within RDM, stimuli by stimuli matrix inference. Second level, we have a lot of these RDM matrices. Now we make comparison between RDMs. That's the second level inference for the RSA. So like this. That's the concept.
So basically, we will have two ideas at least. We'll have to capture. One is RDM, representational dissimilarity matrix.
Basic unit.
RDM.
And we have within RDM analysis. We have between RDM analysis. And these two.
Okay. And the second is RSA, representational similarity analysis. Okay.
So we have this in the more practical sense. We have searchlight RSA. We have searchlight RSA. In the Cosmo we have this searchlight RSA, whole brain searchlight RSA. And the RSA toolbox actually is better for second level RSA in the practice sense, practical sense, not practice. Okay. So that's why I'm going to use both actually. And if I may show some of my result first. Yeah. So this was the RDM that I used for my research, musician research. We have like I compare like musician and non-musicians stuff, and yeah, something like this is pretty cool, right? This is the result of like, so I have this very simple RDM, and I scan each voxels, not scan, like how to go, like I correlate each voxels with this neighboring 100 voxels, compare this matrix. So it's like right now area is like actually correlated with this simple matrix. You know? It's hard to say. It's too much to say. Okay, actually. So yeah, it was pretty cool actually. But anyway, let's. Yeah, I will go back to the real demo part. I guess that's better, to be honest. So how's downloading?
Done.
Done?
Me done. I guess most of us are done.
Oh, okay. Yeah, that's cool. So, Cosmo MP, I will start from Cosmo MP. So, I will get slow. You can follow me. So, we have Cosmo MP master. I already have included the tutorial data and tutorial data out pass. We have to do it manually, so I already did it. So thanks for me, okay? Anyway.
Thank you.
Yeah, you're welcome. Good. So I will set pass, but it's not just set pass. We have to use a tool, the function, Cosmo MP function. So let's see. So Cosmo MP master and MBPA, and open the Cosmos set pass. Cosmos set pass. Here's the function. Open the Cosmos set pass and run. Yeah. And you have to type save pass. Save pass. And we go up. Oh no, where is it? Okay, it's fine. And then we go to, because I'm going to use demo dataset, so we're going to examples folder, open Cosmo wizard set configuration function. Yeah, and run this, and it shows up. I need to set the tutorial data pass. So okay, and we hear tutorial data. Okay, here, and we need to specify output pass, which is another folder I created. Tutorial data out. Click it. And you make sure your tutorial data pass is here, tutorial data out pass is here, and continue OK. Done. Happy Cosmo MPAing. You gotta see this.
examples，再按开启，然后OK，然后现在是examples。
Where's the subpass file?
Surface is in the MVP.
Tutorial data.
MVP. Cosmos surface. And PQRS.
Subpass.
Yeah. And just run it.
就是 input。OK。你要再选 out。
Header must be.
对。
This weird. Okay, we. Yes. Yes. Oh? Maybe you should clear all this.
设定它的目录。
Yeah.
可能等一
This
下旁边的东西要存在 out。
Professor, did you extract it?
不知道你要分开，但是可能
Yes.
Oh, that's weird.
经常。对，它会因素在这边，但是它输出在 out。
这应该也是分抓影子的资料量和抓包括的资料量。哦，
我猜可能等一下，
就是这个配置我们不用再设了。
对，他可能是希望我们先设不同看他们的东西打架还是什么。
然后我们像这个跟这个处理很对，
很复杂，看着复杂。
Yes, you.
Do you need to set the tab?
From this way.
I think that's fine.
Okay, it's fine. Okay, so just need to test for the materials.
对啊，但是它其实应该不会只有口诀选择，它有其他选择，但已经就先用口诀选择来。
他的意思是说，这是他们，不是他在做生育。
看4个世纪，然后是自然史的相关。这个图是影像手一个细胞是一个 那你再看到脸的时候反应相似性，都是不相似性，是比较相似的。然后就是高它们的相似性，因为它一个反应的，它很多只是一个位置，它一个是一个开始，那个25%看到这个事情的反应型的表现，这个25%看到下一张的反应应该是很相似的。
这有点就是反应在一块，然后他就是把人物的确的那个正确的方式，还有修饰的方式，有点像做
对啊，这个猫咪没有，这个没有科学嘛，那这边就是直接告诉你相似性，这假如你有一定数量的猫，对不对？20个猫，或者200个猫，它总共是一个它是一个 number of units 的一个反应的相关性。
然后这个代表相关距离近，
对，距离近表示相关性强。对，所以他刻意用解释型的，不相似性不小，而是相似性高。这个怎么样呢？其他也是不相互相知道吧？就一减掉。
所以是活化反应的。
我觉得那个类似于像他们的一个类似于，因为它现在整合不同的工具，不管是 但是不同的solution，但是它在同样的刺激上做实验，可以用这样的方式做比较。然后呢，再就是说，它不是比较同样是在哪个 model 的基础，那有时候的 response，那你就可以看说你的 model 我就这样子了。另外一个就是model 这个就是我到第二时代中，他就有分享这个东西，然后分享这个东西。你可以想到认知科学，认识神经科学家，他的目的之一是要去了解大脑预测型的，或者是了解什么样的模型最适合解释大脑的情绪，这是大脑一个总目的的其中几项。那他们在做研究，了解大脑，借由不同的方法，然后借由他们的相关性，就看到一些，然后就比如在列出一些可能的 model，看哪个 model 的相似性跟行为也好，跟大脑也好关系最明显，或者说解释量最高。
大脑跟行为的比较简单，
所以很麻烦。我们目前的工具也都有它的限制，但是不否认有几点是他们是肯定的。大脑是很复杂的，很弄一组，然后它的工具目前也很多元，所以这个方法 RS 是用来去探讨这些不同方法都有部分，比如说这些工具，这工具的使用很有容易，然后又很复杂。
这个第四看就花这种对，看见脸，就是它的，
这边都是用 multi-dimensional scale 的 NDS 做出来的画出来的距离，它不是一个很单纯的gradient。
这画法
11:30。
所以能够区分的更好。
它最容易区分是 anime 跟你们，那我现在看你们的第一个的话，对，它看的那个跟那个是在看你们的手。
这个相似性超大，是这样在变出，或者是第四行，就是越打开的相似性，
对，因为这里的反应很相似。
Okay, we good?
Yeah, we're good for the simple one.
Okay, and then we move to the examples and open the. There's a lot of demo already, so we open the. This one. We open this one, and actually you can just run it. Actually, it's fine, and you'll see like at least like 10 figures or something. So yeah, I mean it's cool. So let's just do it, okay? Just run it and see like what's going on.
demo 还是打开，然后就按拉到身上，你就等嘛，不要等，然后最后产生实。这还有几句吗？这还有几句吗？8句。
It takes so long.
因为一开始没有什么写，里面写成说加几放在一起。
而且因为像来它是很多
Wait, this one?
包城市20-30G，这种完全不能看出来。
可是你没有在的时候会不会上上
It's not this one.
Open survival script，知道？Log script。它可能目的就是希望你给自己骗出来。我听过 live script 就是可以自己找一些什么段，因为真的很多段。
Because I confused. So this is not the cool one. I mean, cool one is RSA toolbox actually. Cosmo Phase, the demo was not really cool, but yeah, RSA toolbox is cool, but I'll talk later. And so what we hear, should I explain it? That's a lot of stuff. ，Crap, should I like explain it one by one? Okay, guys. I gotta like say, we gotta use RSA toolbox. I mean, Cosmo FA works, I guess. So RSA toolbox is easier. Just set paths in our usual way. Just go to the RSA toolbox, develop, and just add a whole toolbox with the subfolders. Okay.
Where's the RSA toolbox? Where's the RSA toolbox?
Here's this in the folder that I shared. First, directory. Boom, and demos. Okay.
You mean like add paths and subfolder, set path and then add subfolders. I say toolbox.
Yep.
Develop. And save. Okay.
And go into demo folder. We have 4 demos provided by RSA Toolbox. Let's just run the demo 1. I think I should go step by step here. So here it's just initiating the project, like name and stuff. Yeah, so I'm using demo 1, so everyone just play around. Number of subject 12. So I think they simulate. Yeah, I think they simulate or something. Control variable. What is control? So as you can see, it's the Krakow-scripted neuron 2008. So it's the same. It's the same data that they used in the manuscript we just reviewed. Okay. So we already can see these figures. So this is RDM, okay, and reconstructed pattern, simulated true pattern. Okay. Crap, what is going on? Transpose on ND array is not defined. Use permute. What? Which one is the problem? Sure, dear.
他用这个可以画的是组件差异。
对，这就是除了 anime 跟 anime 的那个新规，
这就是比较实用性。
对，就是 anime 他们
第四，这是第四。
对很久的。
Crap, what is it? I got problem. Like, I got errors.
图纸没有到什么。
存在多一点，你只要有一点都做出来。并不是跑，不是跑那个区段，你是跑那个 selection。你要跑全部做完。
没有啊，我的到一半就。就是会后后置。
我其实好奇的是，你装 MATLAB 的时候，就是你会有些东西没有装。对，因为有时候考要不然就是你的空间考量，像其实我也不知道他会装哪些什么要的一些把，像比如说 statistical 做法，还是什么 parallel 做法。我那时候装也是凭直觉，我觉得有些东西我不需要，像什么 automation 啊，或什么经济预测啊，我不需要。但是有些可能需要。说话可能就会需要。
我当初这是后来突然下载，我原本是载的，就突然用好随便找一个，对啊，加关系。
但是你可以，我也不知道看到你在哪里，我就是拿了在哪里。
啊。
对，你为什么会觉得对，你去都可以找一下，对，或者你要爱上什么，就是查一下disparity在哪一个那个说法，就是你要去 Google 一下 disparity 这个程式。
你是用这个说法，还是应该是我是觉得这是 set 还是 no set？
没有可能。你刚有 add is suborders 吗？
对，
那就是有。对，你已经做了，你已经做了。对，都有。
I remember I troubleshoot these errors. But I just downloaded it again and yeah, I think it occurs again. So crap.
Yeah, 15 figures.
Yeah, it keeps erroring like
so many.
keep causing errors.
Does MATLAB version matters or some necessary toolbox has all to be installed? It also is one thing that you get missed.
Yeah, I think so.
Into trouble. But yeah, you also encounter the same undefined variable disparities. Undefined function disparities.
Yeah, I think I should. Yeah,
I'm
I'm
sure you
pretty
encountered
sure.
that. Is it MATLAB version related or not?
I remember it was part of like this part or something else, somewhere else.
Font size.
Yeah.
Font size?
Yeah, I kind of forgot what was the problem. Or I can just ignore this part. Try disparities. MDS scale.
修饰你真的很同学，每个图都看起来很复杂。对啊，是很漂亮，可是太漂亮的图，有时候你没办法解释。看到不行，看那种图，对啊，这怎么解释？
So is it okay, or you guys encounter errors? Like this, like I think it looked like I actually yeah, I didn't troubleshoot the part, bug part.
I'm fine. I'm really fine. I don't know.
I think it's called Meg, I guess. Is it?
Yeah. But he also encountered a
Yeah.
problem. He is using Mac.
But that's fine, because I will use in my musician data, not for this demo. I just want to show that demo is cool, but I will just explain that. I will use my own data. Because in demo, like our input is fMRI derived data, but basically our real data is in NeuralF or Brain Voyager preprocessed one, and the way we use or way we input the data structure is different, and that's actually like a really practical problem we have to figure out. Same model. Okay, I will use my musician data right now and show how we import our NeuralF preprocessed data for use for apply in CosmMPA or RSA Toolbox. Yeah, we need some processing actually between them. So, did Xiaoshan give explanation for how to try estimation better, or? Like a trial estimation, or not?有吗？用那个 trial estimation 的办法，有。
Single trial estimation
有吗？
对啊，就是 NeuralF 的那个
Cool. Okay, I now like last minute, right? Last minute. I'm going to use this demo museum practice one folder. This is the one that we use for the VMP, like LSS, is the least squares separate the data, which include single trial estimation data.
We went through the intro this morning. Xiaoshan has shown us how to do that for one subject.
Okay, cool.
The NeuralF method.
Yeah. So that's exactly actually we use, but one difference is actually there is T-map. There is like single trial estimation. There is option for estimate as T. For the RSA, we use T-map. Okay, so the result is little bit normalized. Little bit normalized. Okay. But anyway, let's see.
So you use Brain Voyager to estimate T-maps, or
No.
use NeuralF?
NeuralF.
So you have to change the output option.
Mm-hmm.
Okay.
So I will open this Cosmo RSA model, June 26, 20. This one. And actually the input you will see is this one. I have three subjects. And it's like a underline beta, underline T, underline no DM, which I'm referring to no demeaning processing. So I tried some different trial errors, so I'll show you. So in the trial estimation beta maps, we estimate for each single trial, and it consists of like every single trial is in the for one subject, right? We concatenate everything. So there is like how many, like more than like 200 maps, brain maps for each trials here. And for the RDM, for the creating this single subject RDM, we need to average for each stimuli level. So we have like each trial level. Now we turn it into the each stimuli level. So in this musician study, I have 20 stimuli. So I have sorted out for each stimuli 1 to stimuli 20, and I averaged this brain map, each single trial estimation brain map, and now we have 20 brain maps here. So this is stimuli 1, stimuli 2. The value hasn't been adjusted, but just take it, okay? Stimuli 1, stimuli 2, stimuli 3, stimuli 4 to stimuli 20. So this is the average trial stimuli brain map. So it's representing each brain's average activation for each stimuli. And based on this 20 stimuli brain map, we can compute 20 by 20 metrics for each single voxels. So actually we can see this is much clean, like the value like points, like 0.3, 0.5, 0.4. Yeah. There's not much like outlying data. You can see like no like extreme data like a 30, 50, 60, 100 or something like that. Because I averaged and I demeaned something. So there is some little bit of processing here going on. So secondly, such a list. I construct these RDM models based on our stimuli or conditions now. So we have raw models by let me see. Crap, what the hell? One second. Low frequency, low or separate. This is bad. I'm not sure what's going on. I think it's right. not exactly what I want. Okay, anyway, I'll go on. Like, so this, like, all separate and perfectly triton and rough, frequency low, frequency high, frequency interval, frequency different. It's all like a how to construct about this is all like based on the stimuli, the characters of the stimuli, and this was like audio stimuli, so I could like encode some frequency differences or based on their roughness and stuff. This was like experimental design, so I encode this into the RDM, and so there was 20 stimuli, so I can turn it into 20 by 20 matrix here, and this cosmic scale form, cosmic p distance was the function that we used for the constructing this 20 by 20 RDM. And actually, if you see the raw models, you can see the values for how it was encoded. Like it's 20 by 20, but
3.1623 is like a max t value or
it's just p distance value. Yeah,
distance value.
yeah, distance value. It did to scale into 0 to 1 later, but for now it's just for the Cosmo MPA, like here. So let's initiate I equals 1. I have I to 1 to 3, but for here I equals 1. The data loaded and the mask is the one that we use from the NeuralF Tarak ICBM normalized mask. Target is referring the 1 to 20 stimuli. Okay, let me make sure some part. Okay. And so Cosmo fMRI data set. This is the structure that Cosmo MPA used, required to or make a structure, data structures for use analysis or their function. So I just created Cosmo fMRI data set based on our first subject data, brain data, 20 by the 20 brain maps and Tarak mask file and target. And now we have these data structures. So samples 60K, which is from the mask. 20 is what? The stimuli. SAA, FA, I'm not sure what it is, but that's. So first this
stimulus and FA, I think it's called stimulus feature. Sorry, stimulus attribute.
SA labels.
Function attribute.
Yeah. I didn't really specify, but they just create this variables. Yeah. So I turned the dataset type into double type. It's double and single this int this. Yeah, you don't need to like really. And I created this result stack because this part is because I have 6 different raw models, 6 different candidate RDM, and I need to for each this subject brain activation need to correlate with each of this RDM. So first RDM was the all separate. Second RDM was let me show you. Yeah, here. This is the first, second, third, fourth, fifth, sixth. The 6 RDM I used. So I have this 6 RDM. Now I'm trying to correlate with the subject brain activation with this each RDM. So the subject brain activation is not the whole brain. It's like each voxel searchlight, each voxel with the neighboring voxels, because it's multivariate. And each voxels turn into 20 by 20 stimuli matrix. That's now each voxel, the 20 by 20 matrix is correlated with this model RDM. Yeah. All separate frequency interval, frequency different, one by one. That's what's going on here. So let me just show first k equals 1. So here we use the measure as Cosmo target DSM correlation measure, which is we will correlate between these two, brain activation and RDM. Measure argument, center data. Center data is another processing for the, it's another demeaning. So it make it little bit normalize the data. So, and they strongly, actually there is argument that actually strongly recommended to center data, and it kind of reduces effect actually, I guess, for my perception. It becomes like a little bit more conservative, I guess. So centering data, and voxel count is a searchlight number of voxels, and Cosmos spherical neighboring is the two in the, so it define the neighbor voxels for each voxels. So yeah, make it searchlight for each voxels. Yeah. Cosmos searchlight, and it takes some second. It's not that long, but imagine that it is what? It will go like 6 times, and like for each subject. So each like 20 by 20 stimuli correlate with the one subject brain activation of 60k voxels takes 30 seconds, about like 40 seconds. And we have 6 models, then 240 seconds for each subject, and we have like a 30 subject, and yeah, this becomes a lot of time. So actually it takes time, although it looks short. And save the data. So I run this 6 times for each RDM. Then Three minutes. Yeah, it takes 3 minutes.
How is this running?
For each model, one subject, each for one brain, for each model, 6 times.
Oh,
Yeah.
just one subject.
Yeah, yeah.
And you run this for all the subjects.
Yeah, I did it. Yeah, but this, yeah. Okay, now we're about to be done. Okay. Result. So now you see the result. So like we have 6 results. So like results tags have like these 6 structures, and each structure actually contains the result of correlation by whole brain. 60K, 66K, yeah, 66. And if we do it like many times, then what? Like we first we save it, right? We need to save it. The good of Cosmo MPA, like actually they allow to save as a VMP because our input was actually in the target space, so we can actually output as a VMP as well. Let's save it. So we have like one subject. I say result here. I just saved. And if we have like all the subject, then we run the t-test for each model. We can run the t-test each models, and that's it. And that's the result of RSA. For the second level inferences, I'm going back to use RSA toolbox here. So clear all. Well.
Just realized there's an option called quick.
This pretty like a strong one, like forcefully like kill it.
Oh, we sometimes need that.
Yeah. Okay. So I just opened this musician ROI RSA, this function, and I will go further. Keep going. For the second inferences, I already created this math files, so I just load the whole things, and this flag or these parameters is for the analysis. Okay, like I'm going to use Spearman subject random effect, ranked random effect, and alpha is 0.05, blah blah. And for the reference, there's like flow chart for like what you should use for statistics. Like here is suggesting that you can use random effect ranked test, or you can use bootstrapping. Yeah, it's up to like the random the number of the condition and number of subjects. So you can reference this part because I have met the requirement for this random effect ranked test, and I don't need to do the bootstrapping. So let's see how it goes. So what I did here is actually a little bit more complex and more advanced because I wanted to make it into a cluster-based, ROI-based inference, and we did like a 60K each voxel-based whole brain RSA, but I turned into like a 90 ROI, 90 cluster AAL cluster-based RSA. Yeah. And that was another amazing result, I guess. So I provided this AAL stuff, AAL 90, and that's automated anatomical label, and they have like a 90 different. Let me show you. 90 different mask files. Like we have brain and we subdivided like ROI based on their brain regions. For example, yeah, you can see that like this, it's a little bit missing here, but this color actually, this mask color, each brain region actually coded in different number. So we can call each brain region with this number, like 1 or this area, 83, 85, 89, and this whole structure actually can be found, you know. So one is presenter, left presenter, second right presenter, and blah blah blah. This whole brain is subdivided by 90. Actually, the vermis is like the cerebellum part. So we don't need like this part 91 to 116. So 1 to 90 is actually coding each brain regions with different numbers of masks. So later. So I have defined each brain region with different mask files, and I saved it as different files. And now what I'm doing is each brain regions from predefined ROI mask correspond to our each RSA models are the 6 models, and see which cluster actually corresponding to the specific RDM. That's what we did, that's what I did. Result. I didn't include it. Oh. The result is saved in the musician AL90 brain net here. So I will load this data. Why? PR AL90. What? I didn't save it? Can I? Musician stat. PR. It's weird. Or is it different name? I guess it was different name. Can difference so. ROI candidate related SP. Yeah. So yeah, I know like you guys are bored, but yeah, it's quite. What I did actually like quite. You know, like it took a long time. So it took like a year. So this P like corresponding like one each like. The P value corresponds the R into the P. Yeah. And yeah, and this is like the significant, and the node side and edge side is scaled and then represented using the BrainNet viewer, the toolbox. I included in our folder, but yeah, it was something like this. Which representing some brain networks. So this orange activation was RSA result, which search right RSA. So our RDM model to the voxel. Meanwhile, this node and edge was derived from the cluster based and correlated back to which RDM is more correlated. So RDM to voxel and cluster to RDM, this kind of way. And I found like some high correspondence actually, some correspondence in the brain areas, in the musician brains, and that was the result. Yeah, I think it's a little bit much, and yeah.
It's quite cool.
Yeah, I mean I included all the necessary toolboxes, but. I mean, if you need help, I can help, but just play around the demo, okay? That's fine. Just play around the demo, yeah. there's like a lot of demo and data sets. So if you like really want to apply this method to your real data, then you can just you can find me, okay? But until then, play around, okay? Cosm MPA, RT toolbox. That's it. And for the reference, I included how to use the Cosm MPA for our VMP. So it's the trial estimation data with like a trial estimated brain maps. We load the same. It's same like XFF, use XFF and VMP, and you extract their brain data. And this find part is about sorting out with their name, condition name. So we need to like specify each trial map with their name. And this like target is the condition 1 and 2, and chunk is the run part. And because we have all the concatenated maps, so and another the data Cosm fMRI data set, which is data structure, and we run the classify LDA or LIBSM, and we save it back to a VMP, and then we run the t-test. It's so this is MPA search for the Cosm MPA, and you guys can just modify it for the use. Yeah, that's another reference. Yeah, that's it.
Thank you.
Yeah.
Yeah. I actually provided one of the talks that I listened this morning regarding the second author, Mary Murn. She gave an intro in the RSA using the paper that you just introduced. And also she provided the later application to the neural net. She was in the Neural Match Academy introducing how deep neural nets could be applied to the object recognition using RSA as a way to measure the correspondence between brain, model, behavior, and blah blah blah. Yeah, that's quite cool. Yeah. So RSA is pretty much like a what? Toolkit?
Yeah.
A method. Yeah, I think it's like a generalized method could be applied in many different ways. And combining different modality, like you're using fMRI and EEG, and many other researchers use fMRI, single cell, or other kinds of neuroscience data. So you can have some kind of general level of descriptions for testing your model, your brain data, your behavioral data. Yeah. So I think it's cool, and
Yep.
but it's very complicated indeed.